Before we move on to the next set of topics, one more small topic we got to deal with before we move on to that stuff, and that's what if you have an ionic salt solution? Okay, what acidic or basic properties can we suss out of a salt solution? So we're going to look at this from four different perspectives. The first one is the strong acid, strong base perspective. Okay, and remember that when we talked about strong acids, we said that the conjugate base of a strong acid, these are usually ignorable. Okay, remember that, and this was quite a few videos ago now, but when we went through the list of strong acids, one of the things that we noticed was that if you have a very strong acid, its conjugate base basically didn't want to go backwards and pick up that proton. It's happy to be be negatively charged because most likely it was stable the way it was. So the anions that will not affect pH are going to be the anions from the conjugate. These are going to be your conjugate bases from the strong acids. So this is going to include Cl minus, bromide ion, iodide ion, nitrate ion, chloride ion, ClO4 minus, and then you're also going to have sulfate ion, and then the hydrogen sulfate ion, HSO4 minus. Okay, and these two, the last two, are going to be coming from sulfuric. These are the conjugate bases from sulfuric acid. All right, now also being said, you've got the family 1A and family 2A hydroxides yields about 100% hydroxide ion, so the metal ions will not affect pH as well. So the cations that won't affect pH, lithium ion, sodium ion, potassium ion, rubidium ion, cesium ion, cesium 2 plus, magnesium 2 plus, calcium 2 plus, strontium 2 plus, and barium 2 plus. So what we're trying to do is figure out, when we're taking a look at a salt solution, if we can identify a compound, like if we take a look at that compound and we can look at the anion or the cation, and we can knock out that this cation's not going to change the pH, or this anion won't affect the pH, then we have to look at the other species. Will that affect the pH? Okay, and that's what we're trying to figure out. So based on strong acids and strong bases, we know that these are the anions that won't affect your pH, and these are the cations that won't affect your pH. So if your compound has one of those or both of those, it's not going to affect the pH. So what can we say about the pH nature of an equimolar mixture of a monoprotic strong acid with a strong base? Remember, we said that the concentration of the acid was going to be equal to the concentration of the base, so that way the pH would have to be 7. It would have to be completely neutral. So if you got a cation that's not going to affect pH, and you got an anion that will do the same thing, they're going to cancel each other out. The pH is going to be neutral. All right, now what if you have a weak acid along with a negligible base? Okay, so here we want to write the formula for the weak acid, which is the conjugate of the weak base methylamine. Well, that was the methylammonium ion. Okay, CH3NH3 plus. Now, how does this affect the pH of water? Okay, so how does this affect the pH of water? The pH goes down, or if you want to say it this way, it decreases pH. Okay, so if we're going to give the salt of this cation with the conjugate base of a strong acid, okay, what would be the pH of this salt? So what I'm saying is this. We're going to take this compound, this conjugate acid, and let's pair it up with a chloride ion, okay? So the salt would look something like this. You've got methylammonium, okay? And then you've got the chloride ion that's connected to this one. So this is going to be methylammonium chloride. Okay, the pH of this compound is going to be greater than 7. All right, so now it's saying let's write the various equilibria expressions for this compound, for this chemistry. So starting with the methylammonium chloride, CH3NH3 plus Cl minus. Okay, and this is going to be a solid. If we dissolve this in water, it's going to break apart, and we're going to get chloride ion plus the methylammonium ion. Okay. Now chloride ion, we know this is ignorable. Now that methylammonium ion can also react with water. Okay, and that sets up an equilibrium to form methylamine plus H3O plus. Okay. Now, since we also have water, we also have the auto-ionization reaction of water going on. So that means you're going to each H3O plus and OH minus will be in equilibrium with water. Now, here's the thing though. Going back to the second reaction, I'm going to point it out. We produced, when this methylammonium chloride is finally dissociated to the point it's releasing H3O plus. Okay. So because it's releasing H3O plus, that H3O plus released in the second reaction is going to titrate or react with the hydroxide ion in the third reaction. So that H3O plus actually decreases the concentration of hydroxide ion from the third reaction. So in this case, because it's producing H3O plus, we can say that this is going to be an acidic compound. Okay. All right, let's try another one. What if you have a neutral cation and a weak base this time? All right, so we want to write the formula for the weak base, which is the conjugate of the weak acid, formic acid. Okay. All right, so if a formic acid has this formula, okay, the conjugate base of that is going to be this, formate ion. Okay. Now, how does this ion affect the pH of water? Well, it's going to increase the pH. Okay. All right, so that is saying give the salt of this anion with a neutral cation from a strong base. Okay. So again, we're going to go back to this list of ions over here, and we're going to pick one that shouldn't affect the pH. Let's go with lithium just because it's number one on the list. Okay. So you have formate ion, and this is going to pair with lithium ion, so lithium formate. Okay. So that's your equation. We know that the pH of this is going to be greater than 7 because it's already affecting the pH as we saw in the previous problem. All right, so we want to write the various equilibria expressions for this chemistry. So starting with lithium formate. Okay, so this is going to be a solid. We dissolve this in water. We're going to get lithium ion, and then we're going to get formate ion. Okay. Now, again, lithium is going to be ignorable. That doesn't change the pH. So we want to focus on the formate ion. Okay. So the formate ion reacts with water. And that sets up an equilibrium. Formate is going to pick up a proton from water. And so you get formic acid plus hydroxide ion. And again, this one's the biggie. Since you're breaking this compound down and you're eventually forming hydroxide ion, you know that this compound is going to be basic because it's breaking down and giving you hydroxide ion. Okay. And then again, you still have the auto-ionization of water. that water's 2 moles of water will be in equilibrium with H3O plus and OH minus. Okay. So yeah, you've got that. So yeah, we've got a lot of stuff here. So uh we can we so with this equation we need a second equation, we need a KB. Third equation will have a KW. So we could actually solve for the Ka of formic acid if we needed to. Now formic acid, here's our next problem. What is a pH of a 0.20 molar KCOOH solution? Okay. So so we've replaced one of the hydrogens with potassium. Okay. So the Ka of formic acid, normal formic acid, should be about 1.8 times 10 to the minus fourth. And this is looking it up in a textbook in a chart. We can get that Ka. If we need to know the Kb, however, when it's deprotonated. So to get that Kb, we know that Ka times Kb is equal to Kw. So we can rearrange this and solve for Kb. Kb would be equal to Kw divided by Ka. So Kw would be 1.0 times 10 to the minus 14th divided by Ka, which we know is 1.8 times 10 to the minus 4th. So that value should be 5.6 times 10 to the minus 11. Okay. All right, so using this information, we know we're going to work with that second reaction where the formate ion plus water is in equilibrium with formic acid plus hydroxide ion. So initially, you know the concentration is 0.20 molar for the formate ion, and you have no concentrations of those two of the products. To change, you know that the reactant has to go down by a certain amount, and the products have to go up by a certain amount, so that way at equilibrium, you have 0.20 minus X for concentration of formate ion, plus X for formic acid, and plus X for hydroxide ion. All right, I'm starting to run out of a little bit of space here, so let me do this on another sheet of paper, and I apologize. I might be able to do it this way. What page are we on? 130? We are on page 137, so let's add a page. There we go. Yay. All right, so let me write that again. We got this. Formate ion plus water is in equilibrium with formic acid plus hydroxide ion. Okay. Initially, concentration of formate ion was 0.20. Formic acid was 0. Hydroxide ion was 0. We know that formate ion has to go down. Formic acid goes up. Hydroxide ion goes up. So at equilibrium, formate is going to be 0.20 minus X. Formic acid is plus X. And then hydroxide ion is plus X. So if we're writing the Kb expression for this reaction, it's going to be the concentration of formic acid, which is X, times the concentration of hydroxide ion, also X, divided by the concentration of formate ion, 0.20 minus X. And this is going to be all equal to 5.6 times 10 to the minus 11th. All right. So if we apply the approximation, that's saying that X times X, which is X squared, divided by 0.20. So X is not going to change. Whatever X comes out to be, it's not going to be enough to change change the initial concentration dramatically, is equal to 5.6 times 10 to the minus 11. So now we're going to solve for X. So multiply both sides by 0.2. So we get X squared is equal to 5.6 times 10 to the minus 11th times 0.2. Okay. And then if we multiply those two together, 5.6 times 10 to the minus 11th times 0.2, that's going to give us X squared is equal to 1.12 times 10 to the minus 11th. And if we take the square root of both sides, X would come out to be 3.3 times 10 to the minus 6 molar. And so that's going to be the concentration of hydroxide ion. Okay. So from this, we could solve for POH, which is going to be the negative log of the concentration of hydroxide ion. So knowing X, pop that in for the concentration of hydroxide ion. POH would be equal to 5.48. And then to solve for pH, that would be 14 minus POH. So 14 minus a 5.08, and that gives us a value of 8.52. So clearly this is definitely going to be a basic solution. So that's pretty cool. We could, this is taking what we were looking at previously just one step further. We can actually calculate the pH of a solution that's not a traditional acid or base. All right. So going back to our notes here, for the following salts, let's indicate the pH nature of both of the solution. So starting with KCl. Now, K, potassium, comes from family 1A, so we know that that's ignorable. Chloride ion is the weak conjugate base of HCl, so Cl minus is also ignorable. So the pH will be 7. So that salt is neutral. Okay. All right. Let's take a look at another one. You got NH4Br. Now, right off the bat, bromine is also on that list of ignorable anions. So that's not going to change the pH all that much. NH4 plus, however, is going to eventually give off H3O plus. So the pH of this compound is going to be less than 7. Okay? Because NH4 plus, it has to give up a proton in order to become NH3 again. So you're going to form H3O plus. So that's kind of what we're looking at. All right, what about this? Cesium nitrate. All right, so cesium is family 1A as well. Nitrate ion, that's the conjugate. So cesium ion we cancel out because that's not going to affect the pH. Nitrate ion is the conjugate base of nitric acid, and that's going to not be affecting the pH. So again, this one is going to be basic. All right, now what about this one? LiOCl. All right, lithium is family 1A. That won't affect the pH. What about OCl? OCl minus. Well, eventually it's going to pull off a proton from water to give you hydroxide ion. So this will actually increase the pH. So the pH will be greater than 7. And so that's kind of how it works. So yeah, in this list, all we're doing is going through the list and trying to figure out how is this going to affect the pH. What we really should do is write equations just like we did for the various equilibria and see if they're going to produce hydroxide ion or if they're going to produce H3O plus. If they produce H3O plus, then we know that the compound that salt is going to be acidic. If it produces hydroxide, now we know it's going to be basic. All right, now what happens if you got a mixture of a weak acid with a weak base? Okay, so it's saying give this salt made from the weak acid, which is the conjugate of the weak base ammonia. Okay, so the conjugate of the weak base ammonia, that would be NH4 plus, and the weak base, that's the conjugate of the weak acid nitric acid, so that's HNO2, so that would be NO2 minus. All right, so the compound that we're looking at is going to be NH4 NO2. All right, so let's look at the equilibrium for this reaction. NH4 NO2 is usually a solid. If we dissolve that in water, we're going to get NH4 plus and NO2 minus. And these are both aqueous. Okay. So at this point, then we treat these separate. So let's work with NH4 plus. Okay, so NH4 plus water is going to set up an equilibrium. You're going to form H3O plus and NH3. Okay. The nitrous anion, NO2 minus, is also going to set up an equilibrium with water. NO2 is going to grab a hydrogen from water, so you're going to form HNO2, and you're also going to form OH minus. Now, both of these form H3O plus and OH minus. So what do you do in this case when you got a weak acid and a weak acid? That's going to be that's your conjugate acid, and you got a weak base. That's going to be your anion. Well, at this point, we've got to figure out. We got to take a look at what our Ka and Kb values are going to be. So if we look at going back to our reaction over here, we can actually calculate the Ka value. And I'm running out of space again, so I apologize. All right. Let me rewrite this over here. So the first reaction was ammonia, NH4 plus water yields NH3 plus H3O plus. Now we know NH3, we can look that up. That's a Kb value. We can convert that to Ka by taking the Kw value, 1.0 times 10 to the minus 14th, dividing it by 1.8 times 10 to the minus 5th. And so that value is 5.6 times 10 to the minus 10th. Okay. We are going to do the same thing with NO2 minus. So if we take that third reaction, okay, that produced HNO2 plus OH minus. Okay. We know the Ka value, so we want to get Kb. All right, so Kb in this case, and we got to use Kb because we're producing hydroxide ion. Kb is 1.0 times 10 to the minus 14th divided by the Ka value for a nitrous acid, which is 4.5 times 10 to the minus second. That's going to give us 2.2 times 10 to the minus 13th. All right, so looking at these values, which one's bigger? Well, in this case, the Ka is actually value is going to be bigger than the Kb value. And since the Ka value is going to be the bigger one, that means, going back up here, what can we say about the salt and water? Well, we know that 5.6 times 10 to the minus 10th is going to be bigger than 2.2 times 10 to the minus 13th. So the pH is going to prefer to be less than 7. So we know that this compound is going to be acidic. Okay. Finally, one more thing to look at. What if we're dealing with a Lewis acid or a Lewis base like we did before? So here you've got a compound, you've got a complex with aluminum, you're adding a water molecule to it, and so that water becomes, you got a couple water molecules that end up being complex, and you form H3O plus on this. The Ka of this ion, if you look this up, would be 1.4 times 10 to the minus 5th. So because it's a pretty, the Ka value is pretty low compared to others, the pH is going to be less than 7. So what we would notice, what ions with what characteristics could cause this effect? Well, the acid will increase as you go up in charge. So +3 versus +2. Okay. The acid increases as you go down in size. And that means greater charge density. That means that the greater the charge density, which is the charge divided by its volume, the greater the charge density, which is going to tell us that's going to be more acidic. Now, To be honest, this is something that we're not going to really need to know in Gen Chem 2, so I'm just throwing it out there, just kind of connecting some of the pieces from previous sections. But if you go further into chemistry, and especially if you get into inorganic chemistry, this is where this stuff kind of comes into play.